after making a 2 centimeter hole, 2 centimeter deep hole. Assume acceleration is constant. Touching pavement. I think, if I recall correctly, that's close enough to the problem, right?
Yeah, it also has, it says, it has like a, it has a weight, it's like
Oh.
a certain amount of newtons.
Three kilogram rock. Okay, good enough, or did you want to, that's a mass. Did I?
Can we do newtons? Or it said,
Good.
it had it in Newton, yeah.
That work for you?
Yeah.
Alright. What is weight anyway?
The effects of gravity.
Okay. Or it's more specifically, it's the gravitational pull. So Earth, in this case, is pulling 3 newtons down on this rock. How would I find the mass of the rock? Here's the formula.
So W equals mg.
That's the one, yep. So W equals mg. If the Newton is a unit of force, so that can't be a mass. So I have 3 newtons is equal to the mass times the acceleration due to gravity, 9.8 meters per second squared, since this takes place near Earth. And so the math problem is 3 divided by 9.8, which is 0.3 something. 0.31. We'll pretend for now. Oh, someone's about to tell me.
Yeah.
Okay. Units?
Kg.
Yes. If I heard you correctly. kg or kilograms. All right, so it's going to be falling 20 meters. Now, so this is basically, we break it up into 2 problems here. Because we can deal with constant acceleration easily enough. So we're going to deal with the problem of it's falling, and then the problem of it's touching the pavement. So as long as acceleration is constant, we've got tools to deal with it. All right, so we know how far it's going to fall. And I think the first question was how much time is it in the air? All right, so define time. I have a rock falling. I know the distance it's going to fall. The simplest way is to use the formula that Hewitt provides. That is specifically for it starts at rest, because it's dropped, it starts at rest. And the acceleration is the acceleration due to gravity, so it's close enough to constant. So we have delta x is equal to 1/2 gt squared. And so that's 20 equals 1/2 9.8 t squared. Or 20 is equal to 4.9 t squared. Or t squared is 20 divided by 4.9. I assume that's t squared.
Oh.
And then t would be 2.0. Something close to 2.0. Calculators were so much simpler before. They would just sort of darken out because you weren't touching the phone long enough, or in between the ads.
Yeah, 2.2. 2.02.
2.02. Units? Times?
Second.
Yeah, seconds. Now, addressing this as a side note, you could express time in meters, but if you're doing that, it's how far light travels in that amount of time. So it'd be a very tiny number of meters. Since it travels almost 300 million meters every second. Oh, no, so the time would be, in meters would be huge. All right, so we know the time it takes to fall. I think the next question is how fast was it going just before it touches the pavement?
Yeah.
Sometimes that's worded, how fast is it going when it hits the pavement? And some students take that and interpret, well, it hits the pavement, it stops. No, it's just physics language. When I ask how fast is it going when it hits, that means at that moment just before it touches. Considering how picky the language is in physics, I'm surprised they do it that way.
It also says something like, it stops over a distance of half a centimeter. What does
Yeah,
that
that's-
mean?
So it falls to 20 meters, and then once it touches the pavement, in that column, it stops at a half centimeter once it touches the pavement.
Okay.
And the way I've done it here, I did it in 2 centimeters.
Oh, so it just means like a whole, like, okay.
Yeah.
Okay.
I mean, the base doesn't break, does it?
That doesn't say.
Yeah.
So the 2.02, so, the timer was in the air.
Yes. From dropping, letting go to just before touching the pavement. All right, so how fast is it going after 2.02 seconds? Or how would you do it? Solve it. Is there a formula over there for VI equals 0, trying to, for the initial velocity 0, and you're trying to find final velocity? And acceleration is relatively constant. The answer is yes. Either one of those. How fast is it going after it falls? Well, that's the way you would present it. So 9.8 meters per second squared times 2.02 seconds. Because every second, the speed changes by 9.8 meters per second. Or even the velocity changes by 9.8 meters per second. And it does it for a little bit more than 2 seconds. So it's going to be somewhere around 19.6 meters per second is how fast it's going. Does that 0.02 make much change?
19.796.
So that's how fast it's going, just before we suddenly have an additional force involved. Because once we get that additional force, the acceleration changes and it's not constant anymore.
And by additional force, you mean
Yeah, the normal force from the vehicle, absolutely. Is the next question, what's the average velocity?
Yeah.
All right, so what's the average velocity while it falls? Riley is correct so far.
The 9.899.
9.898? Quite possibly. So my average velocity of acceleration is constant. My average velocity is my initial plus my final. Oop, lost the number. Divided by 2, and 9.898 units.
Meters per
Meter per
Sorry?
meter per second.
Yes. All right. So we know how fast we know what the average velocity is. And we also could have found the average velocity by the displacement over time. In other words, we could have done 20 divided by 2.02 to get to this exact same equation. All right, questions to hear? Oh, yes, Sushil.
It also says, from the beginning to just before it hit the pavement, does that change anything? Or-
No. No, that's what we're solving right here, because once it touches the pavement, the additional force comes in and acceleration changes. So that's why, basically, we're breaking it up into two pieces. There's the fall before it touches, and then while it's touching. All right, so we got an average velocity, and so now I believe the next question is, we're now dealing with the pavement. How fast is it going when it first touches the pavement?
Final velocity?
Meaning, sorry? Is it-
19.
That's the one. This is how fast it's going just before it touches. It's also how fast it's going when it first touches. So we know what the initial velocity is for the pavement piece. How fast is it going at the end? No, it does slow down. When you said the same thing, did you mean this? Oh, no. So it starts at 0, it speeds up, it gets to 19.796, and then it starts to slow down again. How it slows down to what? Yeah, it stops. It hits the pavement and stops. So if it starts out, for the pavement piece, it starts out going 19.796 meters per second, and it stops, what's the average velocity? Pardon?
It's fine. Velocity zero, it says zero.
Yeah. In my mind, 0 and not existing are not the same thing.
Right.
So how would you find average velocity? The pieces are all there. I have a feeling that half of you know it, but either aren't confident or just shy. Someone be bold. Say with great confidence how to solve this, whether you're right or not. Logan, it looks like you're ready to do this. How do we find average velocity for the fall while it was before it touches the pavement?
Would it not be the same equation, the initial 0 and then the 19.796? That we just did?
It is the exact same equation. The difference is, the first time VI was 0 and the VF was 19.796. This time, VI is 19.796 and VF is 0. So the thing gets faster and faster and faster, and then drops off very
Would it
quickly.
be negative 19.796?
Still down as positive, so it's still positive. The vase, or rock in this case, vase in the master set problem is going down the entire time. Wherever that voice was coming from. So my V average right there, it's the same number. Now, the first time, it went from 0 to 19.796 in, over the 20 meters. Now it's going from 19.796 to 0 in 2 centimeters. So how would we figure out the time it takes to stop it? What's the relationship between displacement, average velocity, and time?
Acceleration.
It would average velocity, and we don't need to know the acceleration at this point. That's coming up. You're ahead of your time. What's the relationship between displacement, average velocity, and time? Someone can say it. You know what? I'll wait this out. Somebody can do it. I believe that there's going to be someone who's willing to actually speak out loud. Elizabeth here now.
Dr. Fox, what was the question again?
What is the relationship between displacement, average velocity, and time?
Can you repeat that one more time?
What is the relationship between displacement, average velocity, and time?
And you said it's not acceleration?
I'm looking for a formula. Acceleration is not in it.
Is it not the one behind you?
It probably is.
The, displacement equals 1/2 average. Acceleration times time squared.
We don't know the acceleration yet, so that's not the most convenient formula here. Say it again?
The displacement equals velocity average time.
Yep, right there. That's the relationship right there. I know what the displacement is, 2 centimeters. I know what the average velocity is, it's that. Plug and chug. I have displacement is average velocity times time. And just so you know, if this were a calculus-based course, this is still a true statement. So the trick here, though, is we're dealing in meters and seconds, and I gave you 2 centimeters, so we do need to figure out how many meters that is. So how do you go from centimeters to meters?
Divided by 2 over 100.
Yeah. Which moves the decimal point 2 spots. So we have 0.02 meters is equal to 9.898 meters per second times time. Now, sometimes units might look overwhelming, so the math problem we're working on here is 0.02 equals 9.898 t. That's the math problem. And how would you solve for t?
Divide by 9.898.
You get t by itself, so we need to disconnected, so it's that's multiplication, disconnect by division. The math people insist as long as you do it to both sides, it's legitimate. So we end up with 0.02 divided by 9.898.
0.002. No, 02. 061.
Misinterpreting.
Oh, second.
There we go. Having done this enough, when I give the look, sending out vibes of what are the units, and despite the fact that I do it all semester long, I still get, even at the end, for 16-week classes at the end, people are still giving me extra digits. Apparently, my reading skills not going to require. All right, so we now know how the time, and what was there was a last question there, I forget what it was.
What is the acceleration as it stops?
Okay,
From the moment it touches the pavement to being at rest?
all right, so what is the acceleration? Well, how do you find acceleration?
Velocity equals acceleration times. Velocity equals acceleration times time.
So, okay, we can do it that way. There is an assumption in this that the initial velocity is 0 over here, that's the final velocity is 0. So that does affect the answer. More specifically, if the slightly more generalized, assuming initial velocity is not 0, it's the acceleration is the change in velocity over the change in time. So what is the change